So at long last, we're finally ready to transition into our coverage of Java synchronizers. And I'm going to start by giving you kind of a high-level overview of what synchronizers do, what problem do they solve. And of course, keep in mind that in the back of your heads, that discussion we just had about the Java memory model and how the things that Java synchronizers do are there to address some of the intentional, weak, and generous behavior semantics in the memory model. So a Java synchronizer is basically an object, or what might be called a shared object, that's used to control the flow of cooperating threads based on the state of the synchronizer. And we'll see lots and lots of examples. We'll see a cool example that has two threads taking turns writing ping and pong, and they coordinate how they interact in their flow. Synchronization has been around for a really, really, really long time. And it's historically been used to coordinate safety-critical physical processes. So, for example, we don't do a lot of train travel here in the US for a whole variety of reasons. However, if you go to Europe, or you go to Asia, or you go to India, you'll see a lot of trains. And obviously, each train doesn't have its own track. They're shared a lot of times. And you need to make sure that two trains don't end up on the same track. That's a big problem. And so they have all kinds of synchronization mechanisms, like little flags that are signal flags that indicate whether you should stop because the track is in use, or whether you can go because the track is clear. And so that's a very common use of synchronization in everyday life. And you can read this link about navigation in railways to see how synchronizers are used. Java synchronizers are used to ensure that interactions between threads obey certain properties. So these real-world synchronizers are used to make sure that, for example, trains don't crash into each other and cause tremendous damage and corruption. Likewise, Java has synchronizers to make sure that threads obey certain properties as well. So one of the most important properties, and the one that you'll be focusing on in your next assignment, assignment 1B, is not to corrupt shared mutable state. So if you take a look at this link, you'll see why shared mutable state is the root of all evil in concurrent programs, Java included, but it goes beyond that. And we'll talk about some examples in a second, but here's the metaphor to think about when you think about corrupting shared mutable state, things smashing into each other and causing all kinds of damage. So here's a simple example to illustrate this. This is something called the non-atomic ops example. You can read more about it down here. And basically what would happen if you had this counter and you had one thread that was running in the increment method in thread T1 and another thread that was running the decrement method in thread T2, the question is, what's the value of mcount? And the answer is, you don't have the faintest flipping idea because it's shared mutable state and there's no synchronization. So who knows what's going on here? It'll be chaos and insanity for sure. Now, one way, not necessarily the best way, but one way to get some control over this would be to use Java synchronized methods. So in this case, we have a synchronized method. So thread T1 will be synchronized. So it'll get exclusive access if thread T2 doesn't have exclusive access. And so this will yield the correct behavior. I should put correct in quotes here, since mcounter is shared mutable data that's synchronized at a ridiculously coarse-grained level here. So even though we will not end up with data that's inconsistent, it's not a very useful example because one of these guys is just going to grab the lock and then run forever, and the other guy gets starved out. So even though it's thread safe, it's not very useful. Another way to do this, which will give us more interesting behavior, at least more relevant behavior for the example, is to use synchronized statements. This is a synchronized method. This means the entire method is synchronized. This means just this statement is synchronized. And what we do here is every time the for loop iterates, we acquire a lock and we increment the counter by 1, and then the other thread gets a chance because it can sneak in there next, get the lock, decrement the counter by 1. So mcounter will now always have a sensible value because it's being incremented and decremented in a synchronized way. Now, again, this may not be the best way to do this. In fact, I don't think you'd write a program like this in practice. I'm just showing you how synchronization can make sure that the values of shared mutable state don't get corrupted accidentally when threads run without synchronization being used. There's all kinds of other ways to do stuff like this. We'll talk about things like atomic operations and atomic classes later. So one thing that you need to do with synchronization is don't allow corruption of shared mutable data. Another thing to do is make sure that your threads run in the right order, at the right time, and under the right conditions. And this is an example we will again look at in more detail later. It's really fun. This is called the Ping-pong wrong program. And what we're trying to do is we're trying to have two threads that take turns printing ping, pong, ping, pong, ping, pong. But because we don't use the right coordination mechanisms to ensure that these threads run in the right order at the right time and under the right conditions, in this case, we're going to do ping, 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 and then pong, 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 pong. So all the pings take place before the pongs. Not what we want. When we put in the right synchronizers, which in this case will end up being, say, Java semaphore or some Java condition objects, which we'll talk about later, then we can get the right behavior. We can get ping, pong, ping, pong, ping, pong, and so on. So we've coordinated the interactions between the threads so they run at the right order, at the right time, and under the right conditions. We'll also see that there's other variants of these different needs that motivate other Java synchronizers, but we'll talk about those in just a second.